Jacob Bekenstein, an American theoretical physicist. The year is 1972, and he's deep into research on black holes.
But even if you're a theoretical physicist, there's one thing that drives you absolutely crazy: untestability. No matter how perfectly you express something on paper, if you can't test it in the real world, if you can't observe it, you're never truly satisfied.
Bekenstein was consumed by this very feeling. On paper, he had reached a conclusion. No matter what he tried, the math kept pointing to one single thing.
Black holes have entropy.
We've talked about thermodynamic entropy in detail before, but what Bekenstein was pointing to was something deeper. Black holes contain an incredible amount of information inside them.
Yes, even back then, physicists knew black holes contained information, but Bekenstein took it a step further. Through a brilliant thought experiment, he figured out how to calculate the amount of that information.
But to understand this, we need to revisit a fundamental question. What is information? It is, in many ways, the most important concept in all of physics: information. At its core, information is the distinction between things. And fundamentally, we make that distinction by looking at the differences between atoms. When you think about everything around you, every object is made of atoms. And that means every single object is essentially a collection of information. And for every single atom, we can ask one beautifully simple question: is this atom here or not? If your answer is yes, then you hold one piece of information: presence versus absence. Existence itself is information.
So how do you calculate the amount of information? For example, how much information is in the room you're sitting in right now?
To simplify, let's imagine everything in your room, including you, is made entirely of hydrogen atoms. In that case, you could count the atoms and know exactly how much information is there. And what determines that amount? The volume of your room. This is exactly what Bekenstein expected from his thought experiment. When calculating the information inside a black hole, he assumed the volume of the black hole, or its event horizon, would be the determining factor. But here's where Bekenstein froze in his tracks. The result that stopped him cold. It wasn't the volume that determined how much information a black hole holds. It was the surface area of the event horizon. Think of it like the floor area of your room, not the space inside it, but just the surface you stand on. And just like that, another blow to everything we thought we knew. Another strike against common sense. This was devastating because in its simplest form, it meant there's nothing inside a black hole. And we're not talking about empty space here. I need you to stretch your mind here. Imagine an infinite, absolute nothingness. Not just emptiness, a nothingness where even empty space doesn't exist. There's no place. There's no space-time. And remember, for an outside observer, this was already apparent. Nothing actually falls into the black hole. Everything stops at the event horizon. All information was being recorded, and I choose that word very carefully, onto the two-dimensional surface of the black hole, like data written on the floor tiles of your room. After all, how could anything fall into absolute nothingness, right? And this is where Stephen Hawking, building on Bekenstein's work, derived the formula I showed you at the beginning. Everything we've just discussed is hidden within that single equation. The S in the formula means, in essence, black holes have entropy, and A represents the surface area of the event horizon. Expressing all of this in just a few symbols, that's the beauty of science. But let's keep going. And this is exactly where Stephen Hawking's most famous and most controversial claim would emerge, the one that truly turned him into Hawking. Hawking's claim was this: information, the very thing that gives matter its identity, the arrangement of particles that makes something what it is. That information was being destroyed inside black holes. Destroyed forever. Irreversibly. Gone. This was essentially dynamite placed under the foundations of all of physics. Because physics, and science in its broadest sense, owes everything to information. Without it, nothing has meaning. But after years of fierce debates, and even a famous bet that involved a subscription to an adult magazine, Stephen Hawking eventually conceded. He said, okay, maybe information isn't lost after all. And from this, led by physicists like Susskind, an alternative would emerge: the holographic principle. And this is where that word I chose so carefully earlier, recorded, finally makes sense. We don't know what happens to any object that falls into a black hole. We have no information about it. But according to the conservation principle, that information has to exist somewhere. And if Bekenstein and Hawking's conclusion is correct, if the surface area of the event horizon determines how much information a black hole can hold, then the information of everything that falls in might be recorded right there, on that surface. Actually, this is remarkably similar to how our own computers work. All information stored as zeros and ones, written into memory.
And this is exactly where the holographic principle comes from.
What if this principle, the holographic principle, could be applied to the entire universe? Maybe everything we perceive as three-dimensional, including us, including all the information that makes us who we are, is actually a holographic projection of data encoded on a two-dimensional surface somewhere else entirely. We might be nothing more than reflections of data on that surface, like images on a television screen, like characters in a simulation. Could it be that volume, our perception of depth in space, everything we think of as three-dimensional, is nothing but an illusion?
Now, let me try to explain why this might actually make sense. And yes, it might twist your brain a little. We need to talk about the Planck length. As far as we know, it's the shortest possible distance in the universe. We're talking about a length that is 10 to the power of -27 times smaller than a proton.
Now, think about pixels, the pixels on our screens. Every image, every frame of every video is just a combination of these tiny building blocks.
And when you imagine each Planck length as a single pixel, the amount of information you could encode onto a surface the size of an A4 sheet of paper becomes virtually limitless. As a rough example, you could encode the entire city of Istanbul with everything in it onto that single two-dimensional surface.
And yes, with enough Planck pixels, let's call them that, with enough of them, you could encode the entire universe.
To paint a picture of this, and there are quite a few physicists who support this idea, you could think of the universe as one giant supercomputer. Everything we see and don't see might be emerging from information encoded on a two-dimensional screen that spans the entirety of the universe, like a scene from an IMAX 3D movie. We're not talking about the simple technology used in those theaters, of course, but it's a useful way to picture it. And the laws of nature, the formulas we've learned, they determine how the particle information streaming from that screen organizes itself, which molecules it forms, how matter behaves. We're talking, in a sense, about the infrastructure of the matrix. And here's something even stranger. As science fiction as the holographic principle sounds, On paper, it's actually incredibly successful. We're talking about a mathematical model that could bridge the gap between quantum mechanics and gravity, and even explain the Big Bang. When you map the universe onto a two-dimensional plane, phenomena that seemed impossible, like quantum entanglement and the wave-particle duality in the double-slit experiment, suddenly start to make more sense. And we're left with some truly strange questions. Going back to pixels, when you encode the entire universe pixel by pixel onto a two-dimensional plane, maybe all the mind-bending possibilities of quantum mechanics can finally be explained. As you know, right now, we cannot predict what two particles under identical conditions will do 1 second from now. We can only talk about probabilities, and this ultimately drives the final nail into the coffin of determinism. But maybe, just maybe, we haven't reached the most fundamental building block yet. And far beyond quarks, maybe the tiny vibrating strings that string theory describes, hidden within those pixels, are actually behaving in a perfectly deterministic way.
What if, in the great debate between Einstein and Bohr, Einstein was actually right all along?
In other words, there is still so much more to learn. It may sound extreme, but it's a serious question. And as Feynman once said, ask stupid questions, because if you don't, you'll stay stupid forever. These questions might ultimately lead us to the real truth. But there's always a question lingering in the back of our minds, isn't there? What good is this knowledge to me? So when we learn that we might be holograms, what happens? Honestly, nothing. It might not make any difference to your daily life, to your struggle to get by. Your home, your family, your cat, your dog. They'll all stay exactly as they are, just as they always have been.
But we always look deeper. You know that. We have to.
Just as learning about quantum mechanics didn't suddenly transport us into a quantum universe, learning that we might be holograms won't change our reality either. But if you really think about it, there's a world of difference between who we were before we knew these things and who we are after. We'll continue living our lives as we always have, perhaps, but we'll understand our place in the cosmos better. And with that perspective, we, humanity, will have a fundamentally different kind of mind. Understanding both our significance and our insignificance at the same time. As humans, as the universe's way of expressing itself, we'll understand so much better that we are a part of it. Understanding. For people like us, isn't it one of the fundamental purposes of life? And as always, until we meet again, I'm so glad you exist. With love.